So he will talk about exploring collective quantum dynamics using programmable quantum simulators.
So I'd like to thank you, Juan, for invitation and for organizing this. I kind of figured that the format of this meeting will be unusual, and this was an attraction, but I actually did not read his emails very carefully, so I did not realize that I am supposed to give a chalk talk, you know. So, but it's okay. I will give my best. So it was not what I envisioned. Anyway, so I would like to talk today about, I think, very exciting frontier of the research, which actually combines building quantum computers and actually also exploring new open problems in many-body physics. And my plan today is that I will briefly talk about one approach of building quantum computer, where you basically, build this, quantum, systems, controlled quantum systems, atom by atom. I talk a little bit about how we do it using optical tweezers and introduce this idea of Rydberg blockade. So I will then talk about using this system in an analog mode. And I'll introduce something which is called PXP model, and also tell how one could use this analog model to explore both ground state physics and dynamics. And actually, I would like to use at least maybe the last half an hour to talk about kind of a different approach. And this is using digital quantum computers. So I will in particular introduce this idea of reconfigurable architecture. And then I will tell you about how one can actually, in practice, implement these ideas of quantum error correction and fault-tolerant quantum computing, something that theoretically has been around for over 20 years, and now is becoming experimental reality. And actually, in particular, if I have time, I maybe will briefly talk about quantum simulations using these error correction ideas. Okay, so the kinds of systems which I will talk about will involve neutral atoms, which will be suspended and individually controlled in optical tweezer arrays. So what is it? So if you have a focused laser beam, and also join others with apologizing for my drawings. So basically, what will happen is that at the point of there will be a point of maximum laser intensity at the focal point, and if you sort of pick the color of this laser beam correctly, so that you are red detuned, respective to atomic transition, what will happen is that, basically this kind of laser beam will attract atoms. So atoms, like the electric objects, they will be attracted to this point of the highest laser intensity. And if you focus this beam very tightly, what will happen is that this trap will be so small that it actually will be able to kind of house at most one atom. So what happens if you have two atoms? They will undergo something which is called light-assisted collision, and then actually with high probability, basically I have both of atoms, so one of them will be ejected. And so the way how this approach works is you don't just start with one laser trap, but you start with many, and then you basically try to kind of load them all simultaneously. And in practice, what will happen is that some of them will be filled on a given shot, but some will be empty. And so the system has kind of classical entropy, and there is kind of an elegant way to extract this entropy. You just take a picture of the atoms, figure out which traps are full and which are empty, and then you just kind of nearly arbitrary array of atoms. Typically, of the spacing between them, between the straps, has to range, from a micrometer to sort of, few micrometers. So, and this is because you basically need, you need kind of optical resolution here. So diffraction limit, kind of plays a role. But, apart from this limitation, you can basically put the atoms, at least in 2 dimensions, currently kind of in almost arbitrary configuration. And so I'll give some reference. So this idea that you can actually load one atom at a time. It was actually demonstrated here in Paris in Philippe Grangier's group in early 2000s. And this kind of reconfigurable array is actually relatively new. So it was actually kind of done in 2 papers, back-to-back papers by our Harvard-MIT collaboration, and also by Antoine Bravey's group. So I guess it's in Palizo. How do you guys, what's a short acronym? Palizo. PAL. So it's 2016. So, okay, one obvious limitation here is that, when these traps are separated by such a large distance, basically the tunneling between these different tweezer arrays is basically negligible. Of course, there are ways to kind of circumvent it. You could, lower trap depth to allow this tunneling, but that would require, for example, these atoms to be in absolute ground state, which actually is not the case in most of the experiments right now. So, but it turns out that there is another elegant way. So as a result, basically these atoms are completely classical. They're not interacting, they're not talking to each other. So it turns out that there is another way to make them interact. And this is by using Rydberg states. And in particular, something which I'm going to introduce called Rydberg blockade. Kind of the idea here is as follows. So initially, when these atoms are trapped, they are basically in electronic ground state. But what you can do, you can excite, it's called G. So you can excite these atoms into the states with high principal quantum numbers, the so-called Rydberg states. And so the typical kind of quantum numbers one ends up using is something between maybe 30 to 100. So it could be either S or P states. So these are not this kind of low orbital angular momentum states. And the kind of the special feature of these states is that they feature very strong van der Waal interaction. So the van der Waal interaction actually scales as 11th power of principal quantum number. And it's actually, for example, for n equals 100, it's 14 orders of magnitude larger than the ground state van der Waal interaction. And in addition, these Rydberg states, they typically feature a reasonably long lifetime. So for example, the lifetime of these Rydberg states between like 50 and 100 for n equal 1500 is actually more than 100 microseconds. So, so that kind of means that you can actually, if you pick the right color of lasers, or maybe 2 lasers, sometimes it's 2 photon transition, you can drive this transition, resonantly and coherently, and you can, for example, observe many Rabi oscillations. So this is true if you just look at isolated atoms. So if you actually have a pair of atoms, if these atoms are far away, this resonant excitation would still, kind of result in dynamics of 2 atoms evolving independently. But if you bring these atoms together, what will happen if you basically, for example, take a second atom and, and you bring it kind of close together? So then what will happen eventually, this strong interaction will take over. And at this point, if, for example, you start with both of these atoms in the ground states like this, so if you excite them, what will happen is you will be able to excite one atom. So for example, you excite the state GR or RG. But, but if you try to excite the second Rydberg atom, this interaction, will be very large. And so this second level, will be just shifted very far away from resonance. So basically, let's imagine it's, off this blackboard. So And so what will happen under these conditions, is that you will be able to just create one excitation, excite one atom or another, but never both simultaneously. So that's the essence of this Rydberg blockade effect. And this Rydberg blockade, it turns out to be actually a very useful tool because it allows one to, for example, like entangle atoms, or do quantum logic in a way which is actually robust with respect to, both like position of atoms. So long as atoms are under Rydberg blockade, you can basically approximate this interaction as kind of infinite, It's also robust with respect to motion. So in some way, it makes the interaction between atoms digital. So kind of that is maybe one concept I would like to introduce. So it's basically, it's either kind of off if the atoms are far away, or if the atoms are close, it's to the leading order in infinite. So, and that's kind of, it's either on or off. So, and kind of, so that's the idea of this Rydberg blockade. So the statement is essentially that at distances are smaller than the so-called blockade radius, which is actually defined as this, actually, I think maybe it's called C6 divided by R to the 6. All right, so basically, once the interaction is larger than the Rabi frequency, right? That corresponds to this so-called blockade condition, or RB is blockade radius. So, okay, and so that's kind of the idea of the Rydberg blockade. So it's the kind of the theory of that kind of dates back to early 2000s. And it's basically was a collaboration between my group and Peter and Ignacio, group in Innsbruck. And then experiments, the early experiments were carried out maybe around 2010. And actually they were done both here in Paris, in Orsay, plus also Wisconsin. So, okay, so that's kind of these tweezers with the sorting procedure, and combined with this Rydberg blockade. The combination of them is actually forms this approach to building quantum systems, which sometimes is called, tweezer arrays. And it's actually a very exciting field. There are a few hundred experiments being built around the world dedicated to that. There are actually at least 8 companies which are trying to commercialize various aspects of these technologies. So maybe I just, before to complete this kind of overview of this kind of experimental approach, so maybe I will just briefly kind of mention, the current status is that kind of arrays containing over a few thousand atoms have been created. Also, a kind of arrays of over 500 atoms or qubits has been controlled in some way. So, I mean, sometimes people just create these arrays, but they don't do anything. But so, like, already systems of 500 or so atoms have been controlled, also with individual control. So, these arrays can now be very kind of efficient, created in both 1D and 2D geometries. So, and also they involve both alkali atoms like rubidium and alkaline earth. And moreover, even within the kind of given atom, You can have different types of encoding. If you want to encode quantum information, you have a wide variety of possibilities. For example, you can encode in kind of the qubit, for example, in ground and Rydberg state, or you can encode quantum information in two different types of Rydberg states, and it doesn't have to be a qubit. It can be sort of qubit if you want, Or alternatively, you can also encode quantum information in the hyperfine states, in the spin states. For example, let's call it 0 and 1. So in this case, of course, the atoms would not be interacting, but what you could do, you can use controlled excitation. You can basically, with a pulse, briefly excite the atoms to the Rydberg state, and that way to make the evolution. And basically, both of these kind of approaches can be now explored in both analog and digital mode, and for things like, for example, quantum simulations of or quantum computing. So okay, so this is kind of all I wanted to say about this kind of general experimental approach. I'm happy to answer any questions if you guys have. So please feel free to interrupt at any time. So any questions about? Yeah.
You mentioned that the interaction in case of the Rydberg blockade is insensitive to motion.
Yeah.
Is it still the case when you consider geometric phase gates that rely on the hyperfine level where you actually go to the Rydberg state and accumulate phase dependence?
Yes. Yes, and it's actually, in fact, in this case, like I will give an example of this reconfigurable architecture. This can be actually especially powerful because, often, if you study, for example, many body physics, often like these long tails matter of interaction and so on. But if you do, for example, if you have a digital approach, you can sort of define positions of the atoms such that they either, close, and then you do this kind of with this kind of, brief excitation to the excited state. So there, like it's very important actually to the leading order. This insensitivity is very important, and it's actually the origin for, like, for example, high fidelity gates that we and others are now doing. So yeah. So I'll maybe talk a little bit about how we do it. And so basically there, you can pick the places for atoms either to be very close to each other or really far away from each other. So this condition is really satisfied, and then this kind of digital aspect of interaction is actually super important. Yeah. Yeah. All right. Does it make sense? Any other questions? All right. So if not, I will then proceed and talk first about kind of analog approach, analog quantum simulations. And okay, so as I already mentioned, so basically we can pick different types of encoding. So in fact, these analog quantum simulations are pursued using different types of encoding already as is. So I will focus about this on this encoding of basically qubits and atoms, or if you want, spin 1/2 in ground and Rydberg state. But so in this case, we will actually be doing with kind of Ising-like models. But I should mention also that there is another kind of approach, which, for example, involves encoding qubits in a pair of Rydberg states, for example, S and P states. So this approach can naturally result in XY models, and this in particular is pursued by Antoine's group. Let's call it Palizot, starting, I don't know, 2020 now. So, but I'm not going to talk about it. So I think there are a couple of Antoine students here. If you want, if you ask me a question, they can answer for me. So, Okay, so I would like to focus about this kind of ground Rydberg encoding and using this kind of Ising-like model. So basically, the Hamiltonian, which describe this type of many-body system, will be of the following type. So first off, we will be using laser to drive the atom from the ground state to the excited state. So I should have denoted, maybe, okay, let me just do it. So this laser will be described by this Rabi frequency, omega. And so basically, this Hamiltonian we can write in the following way. So it's h bar omega, which can be either global or local. So let's assume for now it's a global driving times x. So where basically kind of x is a sigma x operator, which flips between the ground state and the Rydberg state. So then there will be a term which is proportional to laser detuning, which I will write, which in general can be individual for each atom. I'll write it in this way, where basically I will introduce n. I is basically a number, is a kind of a Rydberg atom operator on the side I. So you can also write it as a in terms of this kind of z, like this. And then finally, there will be the interaction term, which will describe, in our case, it will be van der Waal interaction. So its interaction is on only if both atoms are in the Rydberg state. So this is kind of, that's a basic Hamiltonian, which derives this system. And now, of course, what you can do, you can actually, place atoms in sort of different configurations, and then, play kind of both with this excitation and with this detuning to really try to study all sorts of, possible quantum dynamics. So there is one kind of specific special case which has been studied both theoretically and experimentally quite a lot. So suppose you have kind of nearest neighbor blockade such that this un, we'll call it a prime for nearest neighbors, right? Just call it NNN. Nearest neighbors is much larger than omega, and all other U's are much smaller than omega. So in this case, basically, you have only nearest neighbor interaction, but this nearest neighbor interaction to the leading order can be thought of like almost like as infinite. So, and in this case, this gives rise to something which is called PXP model. So this PXP model, like I will write it kind of in 1D for simplicity, it's a model in which you basically have this kind of driving, which effectively is described by just flipping the atom from ground state to the excited state, and sandwiched between these two projectors, where basically, so these guys are projectors of nearby atoms to the ground state, like this, right? So basically, if and only if your neighbors are in the ground state, you will be able to excite atoms, right? I mean, it kind of follows from this blockade consideration. And so, and of course, then you also have this detuning term, right? So, and of course, if you now go to, let's say, 2 dimensions, right? For example, in the square, I mean, depending on your connectivity, you'll have, P, PP, XP, right? So basically, your neighbors have to be, down for the given atom to be excited. So, And okay, this kind of model is this model or this Hamiltonian describes a class of models which have this kind of so-called constraints. So you will have some certain kind of states, unavailable, certain parts of Hilbert spaces unavailable. So it actually makes them special, in particular for dynamics. So let's kind of talk a little bit about the physics which one can study with this model. And to begin with, I would like to focus first on ground state phase diagrams. So actually, I will do it in 2 dimensions. So, and initially, sorry, second. Oh, wow, that was a mistake, right? That's a mistake. Okay. It's okay. It's okay. All right, it's okay. I will figure it out. Okay, so let's focus on this as some kind of topology, as a problem. But okay, it's all right. It's okay. So let me just kind of, draw the phase diagram for this 2-dimensional array subject to this Hamiltonian. Let me call it star. And there's actually there are kind of a number of phases which can be accessible. So I will parameterize this phase diagram as a function of detuning, and on the other axis, I will put this Rydberg blockade divided by lattice spacing. And so the first case I would like to consider will be square lattice. So A is a period. Okay, so one can understand this phase diagram first by looking at delta, which is negative. So if delta is negative, here you really want n to be 0, right? You want to actually all atoms to be in a ground state. So in that sense, the state is trivial. However, if delta becomes positive and large, what you would like to do, you would like to basically maximize n on each side. But if you if you didn't have an interaction, all atoms would be in excited state. It would be the lowest state with respect to this Hamiltonian. But actually, if you have this blockade, for example, if nearest neighbor is blockaded, clearly you cannot excite all atoms. You will be able to excite only at most half, right? So and basically, this gives rise to the phase, which is probably the most prominent phase here of all, which is the so-called checkerboard phase. And so basically in this phase, what happens is that every odd atom is excited into Rydberg state. So, and each of the neighbor is in the ground state. So that's the ordering. So it's basically, it features, so this is, let's say, Rydberg, and this is ground. So this is the phase which breaks the symmetry. So it will have 2 antiferromagnetic states, and basically with complementary ordering, either this one or the one where the other sublattice is excited. So that actually naturally occurs when this R over RB is around 1. But actually, if you then start increasing the blockade radius, so what happens is not only nearest neighbors will be blocked, but also like eventually second nearest neighbors and so on. And so it kind of gives rise to the family of other phases. So actually, I'll just maybe they kind of look like this. So the second phase is called striated phase. And so in this phase, what happens is that you have a kind of the caricature for this phase is a little bit more complicated, but caricature is that you have still, let's say, these atoms can be in a Rydberg state, But then, so these are Rydberg atoms. So these nearest neighbors will be naturally in a ground state. But then, for example, on this diagonal, this interaction is already non-negligible. And so what happens is that here you end up with the kind of with the atom, which is actually in superposition of the ground and excited state. So it actually there are some kind of quantum fluctuations present in this space, and even if in the case of large detuning when delta is equal to large. And so basically, this kind of this continues. So there are other phases where you sort of have on average, fewer and fewer number of Rydberg atoms per site. So this phase diagram is actually theoretically first described by Subir's group. I think maybe around 2020. And then, it was kind of experimentally first observed. Various parts of that was in our work and also in Antoine's work. It's 2021. But so in all of these phases, you sort of break some symmetry. They're actually different. So actually this one occurs, I think maybe it's just 1.5. Actually phase transitions into all of these phases are also very different. So the phase transition into this checkerboard phase, I will talk a little bit more about it, but it's actually a second order phase transition. It's an Ising of the Ising type. So the transition to other states, actually to a striated state, is believed now to be first order. So, but it's a separate, okay, I could give a separate lecture about this. So, but happy to answer any questions. So does it make sense? And so this phase diagram, can be actually, explored experimentally. What you do, you basically first start with a system at a negative detuning, fix the Rydberg blockade radius, and then start slowly entering into this, to the right side. And then, basically for large positive detuning, you just stop and you take a picture of atoms. You can see, like a symmetry broken state in this case. So that's how the experiments are done. Does it make sense? Any questions? Okay, so, but, of course, square lattice is not the only lattice which one can explore. And I didn't really plan to talk about it, but in light of this morning lecture about the spin liquids, let me just mention that you can create also frustrated lattices, and in particular one which has been kind of very successful is something which is called Kagame link model. So basically what it is, here is that basically you make a Kagame lattice, and you place atoms on the links of this Kagame lattice. So this is, for example, a part. Okay, maybe like this. And so basically, once you do that, and you now pick RB such that each atom blocks 6 nearest neighbors. Some very interesting things start to happen. So you can basically take this model and kind of in the limit of large detuning, where you try to maximize the number of Rydberg atoms, you can map it into basically a dimer model. And so like what you do, you essentially associate each Rydberg atom as a dimer sitting on this kind of current link. Like, so for example, this can be, if this is a Rydberg atom, this would be a dimer. And note that because you now block 6 nearest neighbor, this, and this, so you cannot have a dimer sitting on this link, so dimers cannot touch. So basically, the only other place where you can place the Rydberg atom or a dimer would be here. And then, you know, kind of either here or here, right? There are 2 possibilities, you know, so for example, you can put it here. And then you can also put it, you know, here. So basically what you see is this is, you know, you kind of create what's called, you know, dimer covering, you know, and of course, you know, there is now huge degeneracy in how, you know, which atoms you will excite. So you create all, so you can have in this limit, in the limit of large detuning, you create a huge degeneracy in terms of, you know, these configurations of these Rydberg excited atoms. Note now that there is no crystalline structure here, you know, because basically, I mean, you have like all sorts of possibilities, you know, kind of at least, you know, classically available. And actually, if you then add quantum fluctuations, basically this kind of this driving term, it turns out that kind of under these blockade conditions, with delta larger than omega, what you create in this kind of, in this blockade model. I don't know if you can see it, you know. So you actually, the ground state of this model turns out to be an RVB state, resonating valence bond state, where basically a ground state is a superposition of kind of all of these dimer coverings, you know. So it's kind of it's a coherent superposition of all of these combinations. So, so this actually has been this kind of, and this is spin liquid. It's an example of spin liquid state. So it was theoretically proposed by Ashwin's group, Robin Varsin et al., Ashwin Vishwana. It's, I don't know, it's maybe 2020, something like that, and actually experimentally observed by Giulia Semengini, and this was basically just a year later. So kind of I should say that like maybe a little bit, you know, related to the discussion this morning. So this actually is an example of Z2 spin liquid. So it's kind of has the same universality as a toric code. But for example, to verify that we have this kind of state, you cannot just use local observable. In fact, what we had to do, we had to measure these loop operators and kind of just a little bit of an intuition. So if you, for example, if you make now a loop which, for example, goes around this one vertex here, like a loop like this, so it's very clear that this loop will only cross one of these dimers, right? So the expectation value of Z operators on this loop should be exactly -1, right? Because just only one dimer is excited. So if you now make a loop which covers 2 of these vertices, actually the expectation should be 1. So basically it has this kind of odd-even effect. So it's kind of, it's a bit like a Gauss law, basically. So, and we kind of verified that, but we also verified it in a different basis. So this does not probe the fact that you have the coherent superposition, but if you measure kind of the, if you make a measurement on a different basis, and basically it corresponds to associating some kind of X flip operator associated with a triangle. So one also can measure non-zero expectation value of this kind of loops. And so basically both of them, non-zero loops constitute sort of a positive signature of the spin liquid, and that's what we have actually done. So there is still this is actually a very active field. So the interesting thing, it actually turned out, after we've done an experiment, it turned out that, people now believe that maybe this spin liquid is not actually the actual ground state. So, it means that we might have prepared a metastable state. This might not be a ground state because of long range tails. But so basically things like, dynamics, robustness of this spin liquid, these are all, active questions. So for example, people like Ashwin's group had a follow-up papers suggesting that it's not actually a spin liquid, spin lake, So they have all sorts of fun. So it, basically means that it's a kind of, exists in large but finite kind of spatial region. So this is still an exciting frontier, and basically it pushes both kind of numerics and of course an experiment, and it's kind of the interplay is actually is a very cool field. So, yes?
General question. Does it make sense to study also highest excited states, or they are somehow less stable?
Yes, totally. It's totally, we totally can, right? So there is a kind of asymmetry. Yes, there is. Exactly. We totally can. We can, and maybe I will actually mention a little bit. Yes, exactly. So, hold on a second. So how, I see it's roughly at half time, right? So, okay. So, so basically, Does it make sense? Any other questions? Yeah.
Something known about the timescales to reach sort of the ground state?
Yes, it is also an excellent question. So it turns out the transition into this state is a second order transition. Okay, and so as a result, it actually scales favorably, right? So, and that's why, so we've done experiments with over between 200 and 300 atoms. And so for the system size, we could be sort of reasonably adiabatic. But actually what's kind of interesting is that it turns out that there is in addition to the second order transition to the state, there is a first, people speculate theoretically that there might be a first order transition into the states where this kind of where these fluctuations, so basically it's like these Rydberg atoms or dimers fluctuate in this state, but people believe that there might be, in addition to the second order transition to this state, there might be a first order transition into the potentially lower state where so-called valence bond PBS, right? Valence bond solid, where you basically have this fluctuating, for example, excitations, but they are localized, And so this transition, the first order transition, of course, the gap scales exponentially. That's why we experimentally can just not see it, And so that's like one scenario. But this is theoretical scenario. We don't, because we cannot probe this first order transition, we just don't see it, And so that's kind of part of the kind of intriguing question about that, But so, importantly, this dynamical preparation here is very important. So we never cool the system. The system is closed. We start here on the negative side, with detuning, where all the ground state is trivial, and then ramp and try to ramp slowly, of course, and then study these correlations. And this dynamics is actually very important. Yeah. Okay, so let me now try to operate this amazing system again. So let me now, for the next 15 minutes or so, at least briefly talk about dynamics because of the, So as I already mentioned, basically in most of the experiments, what we do, we have this kind of detuning profile where we start first at a negative detuning. Let's say it's time, and this is detuning, this is 0. So we start at some negative detuning here, and then we kind of ramp it, either linearly, or sometimes we choose some kind of the kind of special trajectory. We basically ramp it from negative to positive value, and the phase transitions happen typically for some small positive value of delta. I mean, it's somewhat larger than 0. Sadly, I covered this phase diagram, but okay, you still remember it. So there is basically, studying dynamics is perhaps the most interesting aspect of these quantum simulations in general. And in this case here, there are few cases which one could study. The first one is this dynamics kind of near quantum phase transition. So the quantum phase transition occurs somewhere here. And basically, by crossing it, for example, at different speeds and different ways, you can really study, like how these quantum fluctuations evolve, what they do. And the simplest, in order to do it, of course, you need to kind of slow change of delta. You need to kind of go relatively slow across this phase transition, that you either adiabatic or you create few excitations, but not too many. So the first the first type of effect at which one can study is something which is called Kibble-Zurich mechanism. And that's, of course, very well known in kind of classical systems. Actually, like in the quantum systems, by now it's kind of like really a standard workforce. But actually, now kind of seeing Tolle, I still remember, what is it, like 15 years ago, he wrote one of the first papers, on one of the first papers on this quantum Kibble-Zurich. And he really had hard time publishing it because people kind of did not believe this will happen. It's a closed system. How can this be? So I mean, okay. So, but it turns out that it's actually really let's say, Polkovnikov, 2004 or something. So what's the idea of this Kibble-Zurich? It's basically the following. So suppose we now have let's look now at what happens. I mean, suppose first we are kind of staying adiabatic, and so what happens as a function of detuning? So you will have some delta 0, and this is this quantum phase transition point. So the characteristic of any kind of second order transition would be that close to this phase transition point, the correlation length would diverge, and this correlation length xi would generally scale as delta minus delta 0. Just put it in absolute value to some power nu. So nu is one of these kind of things which is supposed to be universal. It's kind of critical exponent. So it's universal for a given class of the second order phase transition. So at the same time, close to this phase transition, the gap should also close. And the way how the gap closes, so and this would be, let's say, this is a gap. Basically, the gap generally would scale with the wave vector, but this wave vector should be taken to the power of z, where z is another critical exponent called dynamical critical exponent. And basically, for the basically connecting this K, with diverging psi, one can actually see that this gap would generally close also, close to delta, right? So you just substitute chi as 1 over xi, and so this, will close with the, kind of detuning from the quantum phase transition to the power of z and nu. And so, what is Kibble-Zurich kind of idea? So the idea of Kibble-Zurich mechanism is that that this psi will, as you approach the phase transition, will keep growing as long as the system remains adiabatic. But at some point, the gap will be so small that the adiabaticity will be lost, and then basically the system then freezes out. So the dynamics stops. So this is a hypothesis of this KZM. So that basically at this point the dynamics stops, and so basically by just combining these arguments, so basically dynamics stops at this kind of freezing point. And so what it means is that you will kind of develop, some correlation range, which grows up until it's freezing, and this will scale as a kind of time scale over which you cross the phase transition to this kind of power. So, and this assuming that your detuning is basically a linear function of time. That, basically that's assuming that you go across the phase transition with this linear slope, So this maximal number of correlations would actually be proportional to the rate with which you go, or inversely proportional to the rate, to this power given by this universal critical exponents. And actually, basically by changing the speed with which you go across a phase transition, this Kibble-Zurich hypothesis can be tested. And indeed, experimentally, we measured z equals 1, nu equals 1 in 1D. So this is Kiesling 2018. And actually, in 2D, it's z nu, sorry for this, nice, 0.63. So this is 2D. This is body 2021. So, so that's kind of the Kibble-Zurich story. It actually allows us, in fact, so this, for example, this critical exponent is quite non-trivial. So this is a signature that this is 2 plus 1 d, sorry, this, yeah, 2 plus 1 d Ising quantum phase transition. So these are these critical exponents for this quantum phase transition in 2 dimensions. So basically by using this type of Kibble-Zurich scaling, we can actually study these critical exponents. But actually, it turns out that this Kibble-Zurich dynamics, is only part of the story. And actually, that's what originally I wanted to talk about. But so this would be B. So there is dynamics beyond this quantum Kibble-Zurich mechanism, and this actually is known under the name of coarsening. So coarsening is a, yeah.
Before you go there, can I ask you, in principle, like Kibble-Zurich, you can write in the form of scaling theory. You have equilibrium correlation
We did, yes. No, it's actually kind of what, we kind of do it, normally to determine the quantum phase transition point. I mean, I don't know if this is, it allows us to at least nail it roughly. I mean, I don't know to what extent it can be turned into
It's like extremely accurate.
Yes, yeah, I mean, it is, yeah, so, yeah, there is, I guess, maybe, okay, I think maybe one thing which I should say, I think there is a real opportunity here, and actually I'll mention it, to really do like kind of, if you want, precision measurements of this kind of this phase transition. We've done it a little bit more in 1D, but I mean, in 2D it's also kind of interesting. I mean, it actually, this story that, or this thing which I will tell, actually, you will see also plays a role. And this is a correction to Kibble-Zurich. That's called coarsening dynamics. So in most of the experiments, what we do is we do like stuff like that. So we go across phase transition, then, basically, hold the system for some time. And with this Kibble-Zurich mechanism, basically if you start holding here, I mean, Kibble-Zurich mechanism, nothing should happen. You long ago passed the phase transition, everything is frozen, but it's actually not true. So what happens is this coarsening phenomena, which is known from the classical physics. So basically, it's like if you, for example, like, if you start like, freezing water, right? And you eventually, what happens is that you start like some crystals of ice grow. So what happens if you just leave it at a fixed temperature? There will be a dynamics. And what actually will happen is that these kind of domains will coarsen. They will, like, big domains will kind of absorb small domains, and that's actually a very well-known phenomenon in the classical phase transition. So it actually turns out that, in this quantum phase transition, there is also coarsening. Yeah. Yeah.
Before one actually reaches the complete freezing of the dynamic,
Yeah.
is there any experimental detection observable that one can measure to quantify the level of addiabaticity?
Yes. I mean, there is, okay, there are different ways. Okay. So there is, one way, the one way to quantify it, and it's actually quite good way. I mean, we used it a little bit, in particular in a spin liquid experiment, is to basically do the following. So you can go up a certain point and stop, and then go back, kind of reverse, right? And if it's truly adiabatic, there should be no excitation, but then you can measure, and you can really, it's actually a very nice effect. Again, technical limitations, we cannot evolve forever, so its typical evolutions are, maybe like, go up to maybe 10 microseconds, and kind of the Rabi frequency is, maybe the Rabi flop, maybe it's 200 nanoseconds, so it's like, there are some limitations, but, but this is actually, this is a nice experimental effect. Any other questions? Okay, so this coarsening is something that we actually noticed in this type of experiments already. But actually, right now, we have a few new tools which allow us to, for example, like individually address certain types of atomic patterns, and it allows us to really study these effects, very quantitatively. So, for example, one of the experiments we have done is we created two antiferromagnetic patterns, So, for example, here would be ordering, one type of ordering, like up, down, up, down, up, down, up, down. So here we prepare, for example, another type of ordering, down, up, down, up, down, up. And then we basically let the system evolve. And so, you kind of have a domain, artificially created domain, which you actually can let it evolve, and you try to see what happens with this domain. And actually, this domain undergoes some dynamics. It actually becomes smaller, right? It changes shape. The kind of the sharp corners disappear first, and then it also becomes smaller. And that's kind of manifestation of this coarsening phenomena. So from this kind of studies, by preparing different types of domains, so we experimentally can see that this actually is a curvature driven dynamics, as should be the case for this coarsening. So it's actually, if you look at some kind of, I don't know, some change in some domain wall, for example, position, it actually scales like 1 over r. And what we also see is that basically close to the phase transition, this kind of coarsening velocity accelerates, and it accelerates kind of in accord to this kind of critical exponent nu. So one can really, okay, I mean, this, again, I should caution this, maybe not precision measurement type of experiments, but they really are very much consistent, at least with this idea of quantum, of this quantum coarsening. So this actually grows near quantum phase transition. So that's actually kind of, it's a new work on arXiv, so it's it's a tall, and actually it's a 24/7/03/249. So you can read about that. Yeah. Yeah.
Suppose you could create many of AF2 domains which
Yeah.
are separated from
Yes.
and let the system evolve.
Exactly.
What happens to those domains?
So they grow into the bigger, they grow into the bigger domains. Yes, exactly. Yes.
They would not shrink, like you were saying.
No, okay, no. So what happens is, small domains shrink, and big domains grow, right? So I mean, that's kind of what happens here. It's an extreme version, and of course, then there are boundary effects. The systems are not, huge. They have 300 atoms. One should be kind of careful. So, for example, this kind of universal. So some of this coarsening should be also universal. I should say that in the studies where we create these domains in a controlled way, we actually could really extract these universal features. In this kind of global dynamics, we clearly see that finite size effects play a role. So one can really study these things quantitatively. Yeah. Yeah.
Sorry.
No, that's okay.
So in classical phase transitions, there is something which is called Lifshitz-Liossov. Is that related?
Maybe, yes. So apparently in classical phase transitions, what happens is that the dynamics slows close to the critical point. It's actually a key distinct feature because the dynamics is diffusive near the critical. So, and it's actually, so this, well, but I'm happy to discuss. Yes, maybe we can talk about it. Yeah. Okay, so let me just see. Okay, so. Oops. Okay, well, it's too bad. So, all right, so let me just conclude kind of this dynamics section with a couple of just very brief remarks. So, so Higgs mode was discussed yesterday. And we can actually study this amplitude / Higgs modes in our experiments. We actually kind of observed them a little bit in was a bit of a discovery. So what happened was that when we studied this coarsening and we prepared certain patterns, we observed very clear sort of, coherent oscillations. So, this is so hard. Let's see. How about that? So basically, in this kind of, in these patterns, we didn't see just, like kind of unidirectional flow, but there was some clear oscillations, and these actually signatures of collective modes. So the kind of, maybe the clearest case, how one can observe it is the following. So suppose you, we are now in a square lattice, right? And suppose we pin one of the sublattices to the ground state, and then try to kind of adiabatically kind of excite the other sublattice. So for example, suppose that this is pinned. So this, and this atom is pinned. But we kind of slowly, turn our detuning from positive to negative. So what will happen is that this will rotate this these other atoms, in a kind of XY plane. So actually, it turns out that this kind of procedure prepares, a very low energy state of the system. And the way how we see it, the result is that if we look, for example, for a kind of for a magnetization, so it's an antiferromagnetic state. So we kind of how do you call it? We multiply this every sublattice by -1 side. There is a staggered kind of. We remove the staggering, So basically, but what we see, for example, on the disordered side, if we just prepare the state and then turn off the pinning field, we see that this magnetization actually oscillates. And on the kind of disordered side, it oscillates around 0. Actually, in the ordered side, if we prepared, initially some of this kind of antiferromagnetic looking configuration, it also oscillates, but it oscillates now around. So it oscillates, basically, around some finite value here. So then this is an ordered side. So the oscillation frequency depends on proximity to the quantum critical point. In fact, when we come to a quantum critical point, this oscillation frequency goes to 0, and damping becomes very, very strong. So these are kind of experimental observation. So the physics of that is associated with this amplitude, or sometimes people call it Higgs mode. And essentially, what happens is that on this disordered side, like in a kind of mean field picture, you just oscillate in this kind of mean field kind of Landau potential. So, but on the ordered side, of course, you have a kind of now like Mexico, this kind of double well potential. So you basically oscillate around some finite value of the order parameter, right? That's the order parameter, right? Magnetization. So kind of as already mentioned, close to the phase transition, this the frequency on both sides goes to 0. That's where they meet. Quite interestingly, we can now kind of also using this oscillation, kind of test, for example, like mean field versus kind of quantum field theory predictions. Apparently, in some work which actually originated here at ENS, a few years ago. So some specific predictions were made about the ratio of the frequencies kind of above and below this quantum phase transition. So, and this ratio, kind of just using Landau theory, just using the simple mean field, it should be square root of 2. So these potentials are a little bit tighter. But for example, with the mean field theory, the prediction is that the ratio should be somewhere between 1.8 to 1.9, and it's actually very much agrees with our experiments. So this is actually another kind of another example where one could really try to test this, kind of like do precision measurement kind of type of studies. So, okay, I'm a little bit kind of running out of time, so I also wanted to talk a little bit about scars. So it's actually another discovery that we made. So in this so this collective mode dynamics is quite different from scars. So scars, you create a high energy state. So the way how you do it, you basically start with an ferromagnetic state, and then you rapidly quench it close to the phase transition. In fact, in this case, there are also oscillations that you can observe of water parameter. So these oscillations are of different nature. It's kind of almost like if you throw the piece of ice in the hot water, the ice melts, but then it comes back. So it's very kind of counterintuitive. There is now some understanding of that, and it's actually understanding that for some of these constrained models, you can have this sort of, like very kind of somewhat non-ergodic trajectories where the entanglement basically grows non-monotonically, and it's actually another kind of exciting directions. Maybe I'll just mention here. So this is D would be scars. And so this quantum many-body scars. So this is also, that's kind of, so this is high energy dynamics. Okay, so kind of in terms of open problems, I would say there are actually kind of many exciting kind of directions which one could take. So maybe we can maybe I can leave it for a discussion session, but clearly in terms of ground state physics, there is kind of one big question is to what extent this kind of quantum simulation experiments can supplement, for example, kind of advanced numerical techniques. So these kind of numerical techniques are progressing, very rapidly. But maybe, we were talking with Antoine yesterday. Maybe we could, think about this ground state, experiments as providing kind of samples for training some of these, interesting kind of models. Maybe also for benchmarking numerical effort, but I think this kind of dynamics is actually, I would say, still is a very fruitful pursuit, and there it's the number of numerical methods to really capture these things, is really limited. And so oftentimes, for example, in the quantum scars, like it would be completely impossible to just run large-scale numerics to predict it. Of course, once you know that this effect exists, you could sort of go and build these numerical methods. So I really see that this will be actually a very fruitful ground. Like apparently also, for things like this coarsening, certain types of dynamics, for example, decay of this collective mode is also extremely non-trivial, and it's actually, this is something that we could really do some, precision kind of studies, So this is kind of the analog story. Any questions or comments, or should we preserve them for the, okay. Huh? Yes, yes? No, I would like to continue. Yes, so okay. So I still have half of my lecture remains. But maybe, I hope I'll keep you engaged. Okay, I'll try to be brief. So, yes, yeah.
Maybe just one question. So, as no experimental system is perfect.
Yes.
So, can you quickly summarize what are the source of uncertainties, like the condition of the tweezers?
Yeah. So it really, you have to look at like one specific experiment at a time. So for example, like if we work under this blockade condition, the fluctuations in the tweezers is greatly suppressed. For the other experiments, we don't work under blockade condition is very important. But generally, let's say this type of like Rydberg experiments, so they are limited, the total evolution time is limited by overall duration of the experiment. So there is some dephasing, there is a little bit of spontaneous emission. So, I mean, clearly, all of these analog results at this scale, they have errors. But it is but we have a good control. The error density is very small, but there are clearly errors, right? And so now I think the answer to what extent these things are meaningful depends on what property you are interested in and what questions you're asking. So for example, if you are interested in some kind of absolute, accuracy of certain energies, right? So I mean, clearly, we have errors here which will change it. If you're interested in energy density, I would say what we get here is good approximation. So, I mean, these systems are largely free from disorder. I mean, again, there might be some small disorder, but this is, we can really quantify. These things are really under control,
The disorder is mostly about the uncertainty of the position of the tweezers?
Yes, there could be maybe small, position of the tweezers, exactly, which result in fluctuating interactions. There is maybe some small, inhomogeneity in terms of Rabi frequency, but they are typically, fraction of a percent, and you can make them very, very small if you want. Laser detuning depends on what you do. If you do this local addressing, you could have a little bit of local detuning, but they are quite, the absolute terms, relative terms, they are small, but in absolute terms is hopefully my next part of my lecture. So yeah.
Just to make
Yeah.
it clear, so we can
Yeah.
try to do 15 minutes, and so
That-
as far as you go, then in the discussion session.
Okay, that sounds good. Yeah, I mean, there was some discussion already, so it's, okay. Okay, I will make it kind of quick, but and maybe for this audience, it's a little bit a new thing. But I want to talk a little bit, in part motivated, also related to the question by the one-to-one, about this digital processors, and in particular this quantum error correction frontier. So, and the question I would like to ask, at least, and maybe not answer fully, but can these things be kind of interest, let's say, for many body physics community, and can they really, provide some useful input for the many body problems. So the kinds of things which we are doing in our lab is kind of revolves around something which we call reconfigurable architecture. And this is something which is actually quite unique. And the idea basically is as follows. So let's now focus, instead of encoding qubits in the ground and Rydberg state, we encode qubits in two long-lived spin states, say hyperfine states. So this is kind of similar to what, for example, most of experiments involving spin-orbit interaction, which discussed earlier, are doing. And so in these states, atoms will not interact. They will leave the coherences, leave for seconds, sometimes tens of seconds. Most importantly, if you trap this kind of atom in the optical tweezer, if you move the optical tweezer, this atom will move along with the tweezer, and the coherence, if you do it properly, will stay largely unaffected. So, of course, at some point you need to entangle atoms, and so we will entangle atoms by just using short pulses, exciting them briefly into this, states, into the Rydberg states, and basically just bringing them up and then bringing them down very quickly to just, for example, execute, we like this kind of CZ gate. So the CZ gate is basically an entangling gate where, let's say, one of this, pair of hyperfine states, only both of the atoms are in one state, will get a minus site and all other unaffected. And so kind of with that ingredients, the idea of the reconfigurable architecture is the following. So suppose we start with atoms by placing atoms in some kind of configuration, maybe pairs, or sometimes we put some, triplets, or some, basically we'll distribute atoms in some way. And then, what we'll do, we can individually then address the atoms and basically rotate the hyperfine states, the qubits, and then only if we need to, we will actually excite them briefly into the Rydberg states. And in fact, in most cases, we excite them all together. We have like a zone where we put these atoms, and then we basically just, with the same laser pulse, we can, entangle in parallel, up to, nearly like 300 atoms, in just one shot. But actually then what we can do next is we can basically move, for example, we can take some of the atoms and, move them, kind of to pair them, so to say, with the other atoms, and basically, we change the connectivity. Then again, we can entangle them, we can rotate, and this operation can proceed. So basically, in this way, the connectivity of your processor, if you want, becomes like a living organism. It kind of changes with the evolution without losing coherence. So basically, so this is this idea of this reconfigurable architecture. And it turns out to be very, very powerful. So let me just mention a few things here. So the opportunities is that you can, for example, have, fully programmable quantum simulations and also quantum algorithms. So you can basically now program any interaction if you want. Of course, now you have to do this in a trotterized way. So you have to sort of decompose your involution into the steps. So, but the second kind of perhaps even more special, unique opportunity is that you can actually efficiently implement this kind of idea of quantum error correction and something which is called fault-tolerant quantum computing. So, okay, what's it all about, So as we discussed previously, like our systems are to the large degree isolated, but they're not perfectly isolated. So when we do this, for example, analog, or digital evolution, there will be errors, And right now, I would say in kind of most state-of-the-art system like ours, so the error if you want, per entangling operation, right? So it's kind of easy to define it here in the context of these gates, individual gates, but you can also define it in the case of analog evolution is roughly something like 10 to the minus 3. It's few times 10 to the minus 3. So it means that you can in practice make, thousands of operations, without entangling operations, without basically making an error, which actually is already quite amazing, But the problem is that if you have a large system, and if you really want to make like very high precision quantum simulation or execute quantum algorithm, the actual number of steps you need is much larger. And okay, I mean, depending on the task, this number is different, but it's in any case much, much larger than the current error. And in fact, this error maybe can be improved a bit, but I mean, clearly to kind of improve it to this level is right now no one knows how to do it. Yeah. That's right. So you have to error per operation should be 10 to the minus 9.
If you want to achieve energy, you probably need much less, right?
Well, it depends. If you want absolute accuracy, I mean, it's really related to one-to-one square. If you need absolute accuracy in energy, this, I mean, it depends again on the problem, but I mean, this number has, I mean, okay, maybe it's 10 to the 7, but I mean, it's not, I mean, like this results in systems with low energy density errors, but for energy, I think the errors are enormous, right? Now, it depends on what exactly you want to do, but for example, for chemistry problems, if you want to accurately estimate energy, you need actually more than that, for sort of, yeah. Exactly. Absolutely, there is correct, exactly. So basically, the only way how people in the community believe this can be achieved is by using this this idea of quantum error correction. And quantum error correction, quite counterintuitively, involves entanglement to protect quantum information. So, in fact, my only hope to do it, to explain it in the next remaining 10 minutes is because some of these ideas are not orthogonal to what already has been discussed earlier today. So, for example, this Kitaev toric code has been mentioned. So, the context in which Alexei Kitaev came up with this model of the toric code was precisely this kind of this idea of the error correction. So basically, so example of maybe now the most famous example of quantum error correcting code is this toric, or sometimes it's called surface code. And kind of the idea there is like, it's kind of very similar. It's the same idea as was discussed in the morning today, but it's usually formulated not in terms of Hamiltonian, but in terms of this kind of parity checks of the so-called stabilizers. So basically what you do is you have a lattice in which you put qubits on, for example, links here. And then you basically define your protected space as eigenstates of these so-called stabilizer operators, where these stabilizer operators is basically a product across this kind of vertices, like this, for example, of Z operators, and the products of plaquettes of X operators. So, for example, like this would be a plaquette. So, so this is the vertex, and this is a plaquette. Okay. And so, basically, what you see here is that all of these operators commute because they, like they involve, always at least two overlapping X and Z's, so they commute, and so they define a subspace. And so basically, if all of the eigenvalues of these operators for all of the lattice is 1, this is, people say that subspace is stabilized by these operators, right? So these operators involve the products of 4, Paulis, but, okay, so maybe Hamiltonian is kind of hard to implement it, but, in the digital dynamics, you can just measure it using, for example, ancilla qubits, which you just, let interact with other, the qubits here. And so in this kind of way, you can then store qubits. So, for example, the logical operators are now, in this case, they are products, like Z logical, for example, is a product of all of the Z's going basically from the right to the left. So it's a Z logical, right? It's Z1 to kind of Zn. And X logical should go kind of in the opposite direction. So, for example, like if you look at the product of all of these guys, so it becomes a logical operator, which is just the product of all of these. So these guys anti-commute, and basically you can then store, qubits and protect them by just measuring these A's and B's. So because, for example, if one of them, for example, one of the spins here flips. So, for example, suppose that for example, this guy undergoes the bit flip, So what happens is if you now measure the stabilizers, what you will find is that this stabilizer will be -1, and also this stabilizer will be -1, right? And then basically you know that this error occurred here. So it's basically, you can also interpret these things in terms of like creation. Excitation here is you create a pair of anyons, as was discussed in the morning. So, okay, so why am I all telling you this? So is that, okay, it turns out that if you now take this kind of system and makes it it's bigger, its size larger, then under certain conditions, you can improve how you can improve basically your robustness. So in particular, it turns out, so I mean, if you make a system larger, you have more errors, possibilities for errors, but you also have more checks. So it turns out that there is a kind of a threshold behavior. There's actually a phase transition here. And so basically the logical error rate scales as a probability of error divided this kind of by this threshold in the power of d plus 1 over 2. So d is a linear size of this lattice. So it's called in this case code distance. So it's basically shows how well you are protected in this case. Okay, so that's kind of that's one example of this encoding qubits from physical into logical qubits, and it's actually, I would say, it's this kind of invention of this error correction technique which really gave a push to quantum computing as a field. So it was actually the fact that it's even possible in principle. I think it's totally amazing, but of course these ideas now are like 20, 25 years old. So why is it not the case that all quantum computers use this type of operations? So it's actually turns out that kind of encoding, basically doing quantum error correction, and it means measuring all of these stabilizers, doing gates on these qubits is really hard. All of this is very hard experimentally. And you already see that you basically need to carry some overhead in terms of physical qubit numbers, all of these operations. For example, measuring these qubits, so in principle, if this measurement of the stabilizers, right? So you measure the stabilizers. So in principle, you just, in one shot, if you measure stabilizers perfectly, you can figure out, where errors occurred. But in reality, of course, if you measure the stabilizers, you also use the same quantum operations, so you can also introduce errors. So, and it turns out, in fact, in this story code, normally to achieve fault tolerance, you require d rounds. So you do not just make one round, you need to repeatedly measure the stabilizers d rounds. So it's clearly is a lot of kind of overhead. And so, for example, in terms of gates, it's even more complicated. So because for gates, what you need to do, you need to start basically with, like two of these, kind of patches. And now your quantum information is delocalized over this entire patch. So actually, to make the gate, almost by definition, you need to somehow make each kind of physical qubit feel the physical qubit on the left. And so, for example, like one kind of maybe intuitive idea for this audience, what you could do, you could try, for example, braid anyons. And to braid anyons, you can take the excitation, you need to carry all the way around the other anyon, right? And it's clearly kind of costly. It involves a lot of operations. That's actually one reason that you need d rounds, it turns out, d rounds of error correction. So, okay, so the kind of way around it, turns out, is something which has been actually known also, but people really underappreciated it, is something which is called transversal gates. And so the idea of this transversal gate is that each pair of atoms in 2 patches, in 2 logical qubits. Basically undergoes the same operation. So for example, if this atom, which for example sits here, undergoes the same, undergoes some like entangling operation with this atom, and this atom, with this atom, and this atom, with this atom, and etc. So if all of them, if you bring them together basically and do the operation on them simultaneously, you can, for example, create this kind of, for example, logical CNOT gate. And this actually is possible in the case of this reconfigurable architecture, because what we can do, we can just take this patch, bring it on, on the top of this, and just entangle atoms and just with one laser pulse. And so basically, in this case, all atoms undergo same instructions. So it's very efficient from the point of view of control. You basically can think about this entire patch as one like macro atom, which you can control. And most importantly, it turns out that this transversal gate operation is inherently fault tolerant. So what I mean by that, so suppose you do this thing, and suppose you have a bit flip. Suppose you have an error here, which you did not detect. So if you do that, this error will propagate to the other qubit, but it will propagate in a highly deterministic way. So if you then later, in a later process, figured, oh, I had an error here. So, oh, since I had an error here, because I just only made this guy interact with this guy, I know that this likely will, this error propagated here. So as a result, it's actually much more efficient from the point of view of error correction. So in fact, it turns out that one round of kind of error correction after each gate is sufficient. And in fact, it kind of, these observations, result in a sort of new, so it's kind of, and this is versus normally what you need, normally you need D rounds. So that's actually the idea behind something which is called algorithmic fault tolerance. And in fact, if you want to read, you can take a look at the recent preprint, Okay, so basically, the kind of the moral of the story here, so is that using this kind of reconfigurable architecture, and this is, you can basically implement these gates transversally, and kind of, you can really implement these things in practice, quite efficiently. So let me just use just 1 minute to kind of to finish the story here. So, okay, let me I'll just erase, Okay, so why am I telling you this? And is this all kind of just some kind of children's game in a sandbox, or can these things be useful kind of for the humankind on a time scale which is actually relevant for all of you guys? So let me just finish with the challenges and opportunities. So, and in particular, if I focus on the problem of quantum simulations, one thing which, and like, quantum simulations, now you can do either with physical qubits or logical qubits. So clearly, with physical qubits, you can have a lot of qubits, but you have, operations which are not good. Logical qubits, you have to, pay a price up front. But actually, this is not a full story. So it turns out that the way how this, for example, things like quantum simulations behave with physical and logical qubits are very, very different. And let me just give you some examples. So if you, for example, think about 1-qubit operations, just, for example, simple kind of Rabi flops or phase rotations. For, yeah.
Maybe give him 1 or maybe 2 at most, and then save some more for
exactly.
the question.
Yes, that's exactly. So that's my exactly plan. So
we can take a break.
Yes, sorry about this. So basically, so this is, for physical qubits, it's easy. It actually turns out to be, for logical qubits, quite hard, especially if you involve something which is called non-Clifford operations. And I will leave it to the questions too. At the same time, so if you want to do operations on multiple qubits, for example, kind of things like free body interaction, so in the physical qubits is actually naturally quite hard, but actually it can be very easy. And I can give you an example in the question and answer time. So in fact, in a recent experiment, we have done experiments with 48 logical qubits, with CCZ gates, which is a free body interaction, which actually also is non-Clifford, And moreover, for things which are actually kind of maybe interesting for this community, so things like, for example, fermions. Usually, people believe that simulating fermions with spins, with qubits, is very hard. And of course, sort of the reason is that normally you would invoke some kind of Jordan-Wigner, which becomes non-local or all sorts of things, So actually, with logical qubits, it's kind of unknown, but maybe, probably, it's actually not so hard. And so one kind of answer, you will say, why is that? Well, the reason is this thing which I erased, like the naturally quantum error-correcting codes are often formulated in terms of things like anyons. So anyons, have non-trivial statistics, and this is exactly what fermions needed. So there can be actually very efficient ways, it turns out, or people are thinking about efficient ways to do it. So I think this is actually really kind of, quite kind of special opportunity. And I think this what the kind of the key kind of opportunity here is to think in this approach of co-design. So if you have a problem or algorithm or simulation you want to run, you should think about it in a combination with quantum error correcting code, with what your hardware can do. And some of these things can actually be kind of a relatively near-term prospect. Okay, so sorry for running over time.
So then I would suggest that we stop, reserve some questions, right? Let's take a break and then come back. Thanks all the speakers for the nice talk today.